Okay, so in this video, we're going to take a look at concentration time graphs. Okay, and here we have the Haber process. So we have nitrogen gas in red reacting with hydrogen gas here in green to produce ammonia gas. And another important thing to note about this reaction is that the delta H is less than 0. The delta H is negative. So we have our closed system, okay, and to that closed system, we're going to impose some changes. So at T0, we're going to add equal moles of nitrogen and hydrogen gas to the system. At T1, we're going to add some nitrogen gas only to the system. At T2, we're going to double the size of the reaction vessel. And at T3 here, we're going to increase the temperature. And we're going to see what impact that has on the separate concentrations of nitrogen gas, hydrogen gas, or ammonia gas. So let's take a look at the first one. So at T0, we're going to add equal moles of nitrogen gas and hydrogen gas to the system. Well, initially, there's nothing in our closed system, okay? There's nothing in there. So when we add nitrogen gas and hydrogen gas, we're going to increase the concentrations straight away. So here we are here for nitrogen gas and hydrogen gas. And they sit right on top of each other. And something that a lot of people get wrong, and this is important, is that initially there's no ammonia in our system. Okay, so we haven't actually, our reaction hasn't proceeded yet, so ammonia has a concentration of 0. We only have nitrogen gas and hydrogen gas in this system. Now what's going to happen is we're going to favour the forward reaction in this case. So hydrogen gas is going to get used up, okay, like this, until it reaches a new equilibrium at TE1, so the first equilibrium. But the important thing here is nitrogen gas is also going to get used up, but only at a third of the rate, okay, because there's only 1 mole of nitrogen being used for every 3 moles of hydrogen. So there's a distinct stoichiometric ratio here that hydrogen gets used up 3 times at the rate at which nitrogen gets used up. So we've added nitrogen and hydrogen gas. Le Chatelier's principle says we're going to favour the forward reaction, okay, which means we're going to increase very slowly the concentration of our ammonia gas. And this is going to increase at 2 times the speed in which the nitrogen gas is decreasing. Okay, again, because of the stoichiometric ratio. So that's something really important to keep in mind when we're doing these concentration time graphs. And well, what happens is once we reach this TE1, we've established a new equilibrium, so the concentration remains unchanged. So here the concentrations remain unchanged until we hit T1. And what happens at T1? T1 says that we're going to add some nitrogen gas only to this system. So what's going to happen to the concentration of nitrogen gas? When we add nitrogen gas, this concentration increases very sharply, okay, almost vertically. And then, well, what's going to happen? Le Chatelier's principle predicts that if we add nitrogen gas, we're going to favour the forward reaction in this case because we want to use that nitrogen gas up. So this nitrogen gas is going to get used up. Something like this. Okay, until it reaches a new equilibrium. Now, the hydrogen gas is also going to get used up, except it's going to get used up at 3 times the rate of the nitrogen. So we need a much steeper curve there for the hydrogen gas. And the ammonia is going to increase, okay, it's going to be produced because we're favouring the forward reaction at twice the rate at which nitrogen gas is being used up. So bigger than nitrogen, but less than hydrogen there. Okay, so something like that. And then what happens is the concentrations remain unchanged to this T2. So once we've reached a new equilibrium, concentrations remain unchanged. Now what happens at T2 is we're going to double the size of the reaction vessel. So if we double the size of the reaction vessel, all of our concentrations are going to essentially halve themselves. Okay, we've doubled the size, then they're taking up, or they have more room to move in. Okay, so we've lowered the pressure. So what's going to happen is these concentrations are going to all decrease. So decrease by about half of where they are to start off with. Something like that. Okay, now what's going to happen now is because we've doubled the size of the reaction vessel or we've decreased the pressure, we're going to favour the reaction that produces more moles of gas. In this case, it's going to be the reverse reaction. We're going to favour the production of nitrogen and hydrogen gas. So slowly, this nitrogen gas here is going to increase. okay, until we reach that new equilibrium. And our hydrogen gas is going to do the same thing, but at 3 times that rate. Okay, and our ammonia here is going to decrease because it's going to be used up with favoring the reverse reaction at about 2 times the rate of the nitrogen there. And that's probably, this nitrogen's probably a little bit big. Okay, make this nitrogen a little bit smaller. So something like that, okay? The important thing to note and take away from this is that we have to get these stoichiometric ratios correct. Now, the concentrations here are going to remain unchanged, okay, once we reach that new equilibrium. So up until T3, where we impose our third and final change, nothing is going to change in terms of concentration. Now we're going to increase the temperature of this system at T3. If we increase the temperature of the system, we're going to favor the endothermic reaction. And here it says that the forward reaction has a negative delta H. In other words, the forward reaction in this case is exothermic. So again, we're going to favor the reverse reaction. Okay, so favoring the reverse reaction, we increase the concentrations of nitrogen once again. Okay, and notice how there's no sharp peak in this case, because it's just an increase in temperature. Initially, there's going to be no concentration change. Okay, so it's going to be a nice curved line like that. And hydrogen is going to increase at 3 times that rate. Something like that. And ammonia is going to decrease in this case at 2 times the rate of nitrogen. So something like this. So by the end of it, we don't have much ammonia left there. So that's pretty much it for this video in terms of concentration time graphs. The key takeaways, and we'll write them in pink here, okay, is that you have to get the stoichiometric, and I apologize if I haven't spelt that correctly, ratios correct. Okay, so they have to have their gradients of these curves, okay, we have to have the stoichiometric ratios correct. Second of all, okay, is this point here at T0. Don't get that bit there muddled up, okay? So initially, in a lot of questions, not all the time, initially in a lot of questions, look out for the concentration of the products being 0. Okay, so that can catch a lot of people out. And the last thing that I'll add is to make sure that you get the initial changes in concentration correct. Okay, so if we're going to add nitrogen gas in, then we get this super sharp peak straight away. If we're going to double the size of the reaction vessel, then immediately our concentrations are all going to decrease. Okay, but if we only do something like increase the temperature, okay, then that's not going to have any impact on the concentration initially. So there's going to be no sort of sharp peak here or sharp decline there. It's all going to happen over this time frame like that.